Alright, welcome back everybody. I'm going to go ahead and finish up the sections that we haven't yet covered. On the screen you see section 8.8. This was the last section that we talked about. Alright, so let's go ahead and summarize what was discussed. In 8.8, one of the main things that we had discussed was this idea of a buffer. And so for us, the buffer was essentially one of those reactions, or excuse me, one of those solutions that was very good at resisting changes to pH. So this is kind of what's in this section here. Now the reason that it's able to do that is because whenever the weak acid is in the solution, the weak acid is predominantly going to be in the protonated version. So that means that you're going to have a lot of HA. So you can see that example right here. You can see that it's going to be in this HA version. And so when you add hydroxide to the solution coming in from, say, some sodium hydroxide solution or any other compound that has OH in it, that OH that comes into the solution will react with the weak acid, but because the weak acid has a hydrogen attached, the hydroxide and the hydrogen then will go quickly to produce water. Now we already know that that's going to have a high Ka value, or excuse me, a high K value, and so that'll go very favorably forward to produce the water. Now from a reaction point of view, or within a titration, remember that the titration, you're not going to see a lot of change into the pH. And so at the beginning of the titration here, you're going to see that the curve there that designates the pH is going to be pretty flat. All right, so let's kind of do a little bit of a graph. Let me move this over to the side. So what does that really mean? What does it look like? So if we have the titration curve, and let's go ahead and put one of them over here on the right-hand side. If we've got the titration curve, you're going to have a curve that kind of resembles this general curvature. So overall, though, what you're going to wind up seeing is that it's in this region here, this region at the bottom. Let's go ahead and color code that or identify. Since we know that the pH is over here on the y-axis and time is going to go over here to the right, we're talking specifically about this region here. I'm just going to go ahead and put a box around it. This right here, this section is known as the buffer region. And so the reason that's important to us, because that is exactly what a buffer is going to be doing, this weak acid or this weak base. The one represented here is for a weak acid. Now if it were a base, then it would be the opposite. You would start at the very top and it would make its way down. But proceeding with this example here, so what's happening here in this buffer region is that the weak acid is combining with the hydroxide that's being added and is going to produce water. Now you will have some conjugate base buildup from this point here all the way through. But at the very beginning here, it's not a lot, and it continues to build and build and build and build until you get here. In this buffer region, any hydrogen that's in solution attached to the weak acid is going to bind with the hydroxide to produce water. So you're not going to get very much protons in solution unless they've actually come from the actual acid themselves, but most of it is in the HA form. You're not going to have any hydroxide in solution in this region here because it's reacting to produce water. It's not until you get to this region right over here at the very end, which is essentially the equivalence, the half equivalence point. And just to remind us, how do we get there? Well, assuming that the equivalence point is in this region here, represented by the green line here, what we're going to need to do is we're going to measure the distance down. Halfway through there is the second area, and then we'll just go backwards. And so it's this point here that I'm going to go ahead, I guess I'll point to it with a yellow line here. That there is the half equivalence point. So I'll just write that down as half EQ point. It's this point that will designate the point where the maximum effectiveness of the weak acid is going to be. In other words, that's the maximum buffering capacity of the weak acid. It's the upper limit. But all this region here essentially is the good buffering capacitance. Very high capacity for buffering down here, very low as it approaches the point. And once it reaches this point, that point there specifically is the point where the pH is equal to the pKa of that weak acid. So what does that mean? That means that when we start to see how the buffer is going to work, any point increase into the hydroxide concentration above this point upward will dramatically change the pH, and you can see that. Let me change the color of this thing here. You can see that in this region here. Notice how the pH changes dramatically as you go up from this half equivalence point. Now, the other thing that this means for us is going to be, well, how do you determine that there's a buffer that's very effective? Usually the buffer that we want to get, you want to pick a buffer that will get to this effective range within this pH target. So if the pH target is here, for the sake of argument, let's say it's a pH of 2, then an effective buffer is going to be one that you pick that would be within the range of 3 and 1. And so that will give you the highest buffer capacity or buffering range of that particular buffer. Okay. Now, other items that we talked about previously, what we had talked about here, if I move this up, we had also talked about the question about the what conditions do you want for this buffer? Well, the plain simple thing is, if the buffer, the weak acid, is doing a good job at neutralizing hydroxide in this region, what you want it to do is you want that to be in a good ability to neutralize the hydroxide, but it can only do so when it's in very high concentration. You want it to be in excess. And the reason we want it to be in excess is because if it's plentiful, then you're essentially preventing it from becoming the limiting reactant. And a limiting reactant, as we already know, is going to limit its ability to produce the product, in this case water, because it's in short supply. It will run out. So you definitely want it to be in excess. That's what the general role of that weak acid is going to be, but only if it's in excess. If it's in limited supply, then it's not going to be a very good buffer. The last question that we considered here is, what happens when you dilute a weak acid? And the simple answer here was, if you dilute it, that's not going to make a change at all to the pH. Largely, why? Because you're essentially just changing the volume in the equation. And so if I come over here to the right-hand side, let me see if I can move this up. On the right-hand side, what we've got here is, remember, big M is the concentration molarity, so this is going to be the number of moles divided by a given volume. Well, if you're changing the volume, let's say that the volume is already this. Let's do an example here. What if we had a molarity that was 2 molar, for example? So that means here that you would have, let's back up here, we would have 2 moles, but in 1 liter. Right? Now, overall, the amount of acid in there, the number of moles that are in there, doesn't change. So if I were to increase the volume here, so let's say that I come in here, instead of 1 liter, I change this to 2 liters. The end result of that change is that in the numerator, sure, I'm still going to have 2 moles of that solute, but now in the denominator, I'm going to have 2 liters. So that will change the concentration, but what I want you to pay very close attention here is the fact that we still have 2 moles. Even after we made the dilution, the amount of hydrogen hasn't changed. So pH is not going to be impacted, because if I take this amount here in terms of the number of moles, that's not going to change anything for pH. However, we now have a limited amount of HA, the protons, for example, that are generated from that 2 mole scenario. You've got less protons in a given volume, because now what we've done is we've effectively gone from 1 liter to 2 liters. You've effectively increased the volume in the space, and what that's done is that essentially is creating a situation where, sure, you might have the same number of protons available for neutralization, but they're spread out over a larger area, which makes it less effective. So the buffer capacity of that particular acid goes down. Now, I did provide you an example in class, kind of equating it to a concentration of a gas, kind of looking at it from a density point of view. And if you can understand the relationship there of a gas, that when you increase the volume that a gas is under, you essentially decrease the pressure. But if you decrease the volume in which that gas is under, then the pressure that's being exerted by the gas increases. Largely here, again, referring to the spreading out, in the smaller volume, you got more collisions occurring between the gas particles, which increases the pressure. Here, you've got a similar thing going on with the acid, where the volume is a 1 liter. pressure, or here the concentration effectiveness is higher. But if you dilute that to 2 liters, then the pressure or the effectiveness of the acid goes down. So that's the common question that may show up. But that's what we had talked about in 8.8. Let's go ahead and move on to 8.9. This is one of the sections that we had not talked about specifically in class, even though we did bring up the topic numerous times when we talked about the weak acids. And so this was literally talking about the Henderson equation. And so Henderson's equation is an equation that allows us to kind of look at how to calculate the pH of a given scenario here. And so what we've got is we've got an expression. What providing you here is a sample expression. Here's the expression here. And if we have an expression here for the generic equation, let's go ahead and bring that equation forward. I'm going to go ahead and put it up here just so that it's shown clearly for you. All right, so what I decided to do is I decided to write the equation over here on the right. So let me go ahead and put it here. I think it'll move around if I keep writing it over the text. So what I'll do is I'll just leave it over here. So this equation here, the dissociation of the weak acid, you can see that the K expression is written here. So the Ka expression, since we are dealing with an acid, it's a Ka value. And it will generate the proton multiplied by the concentration of the base conjugate divided by the Ha, which is the weak acid. So that means that when we come through here, we can actually look at the Ka expression. And the main thing that we're trying to do here is to get to this proton. Now, we derived this equation before, so what you see here is the derivation of that process. And if we write the equation for the concentration of hydrogen ion, we'll cross multiply here, getting the values on the right. We'll still get the proton concentration, the base on the right. And then we isolate the proton concentration, so we'll divide by A on both sides. That'll give us this equation here. And if we take the log of both sides, now from this section here, that'll allow us then to get the precursor step to the final Henderson equation. So notice here the log of the concentration, that's just going to give us the pH value. And when we take the negative log of the Ka value, that's the pKa. Now, given what we just mentioned in the previous section, this tail part becomes significant for us now, because if the relationship between the base and the acid is the same, and this is what you're going to find at that half equivalence point, then this whole section of the Henderson equation becomes 0, meaning that at pH that is equivalent to the pKa, that is the threshold for the maximum effectiveness of the buffer. That's the upper limit. All right. So that's essentially what's happening here in 8.9. It's not something new. We've dealt with this problem before, or this particular concept. We've used it, and I've got a sample problem for us over here that I'm just going to go ahead and put in the screen. You can go ahead and pause it here, see if you can answer it. I will go ahead and solve it. I'll pause for a couple of seconds, and then I'll proceed. All right, so let's go ahead and do that. Let's get rid of this part up here, and let me go ahead and position this up to the top. All right, so let's go ahead and identify the key parts here. Some of the stuff has already been underlined for you. We know we have a buffered solution, so that there alone tells you that you're going to have a weak acid or a weak base. So if we keep reading here, we notice it says that solution contains a specific amount concentration of the acetic acid. That is your weak acid. How do we know it's weak? Take a look at the K value, which has already been underlined. The K value is a -5 exponent. That's pretty low. And they're also giving you a concentration of this thing called sodium acetate. And so the sodium acetate formula is provided. And so what they're asking us to do is find this pH. Okay, so if we know this, we can go through it several ways, but obviously we just got done pointing out that in 8.9 we're dealing with Henderson's equation, so that's the point that we're going to start with. So let's go ahead and do that. I'm going to go ahead and get a colored pens here. And so let's begin by first writing the Henderson equation. So Henderson's equation is the pH is equal to the negative log, and this is going to be the negative log of the Ka value plus the log of AHA. That's just a little funny way of saying it, but it's A for the base, Ha for the weak acid concentrations, and it's that ratio at the very end that's going to be key to us here in calculating the pH. Now, since we are provided with a K value, notice the K value is right here, all I'm going to do is just going to plug that in. So in this particular case, I'll take the value here and I'm just going to plug it in right there. So equals the negative log of 1.8 times 10 to the negative 5. And I'm going to go ahead and add that to the log of the ratio between the concentrations of the base, which is at the top. Let's go ahead and label that there. That's your base. The top, and then the bottom part is your acid. And so in this particular case, the acid is the acetic acid, so it's the concentration of this compound, which is 0.5. And so we'll go ahead and put that in the top here. For the acid, it's going to be not on the top, but rather on the bottom. That'll be your 0.50 at the bottom. And the concentration of the base, they gave us at 0.5, so that will go here in the numerator. And so 0.50. And so you can see here under this scenario, the concentration of the base is the same as the concentration of the acid. So this is indicating at this point that we are at the half equivalence point because the ratio is a ratio of 1. So if we do this here, this will cancel out to 1, cancel 1. So this whole unit here, the log of 1, essentially boils down to a value of 0. And if we add that to the log of the 1.8 to the negative 5, it's going to be a little bit less than 5 because 5 is the limit. But notice here the coefficient is above 1. Plug it into the calculator. Take the negative log of that value by simply plugging it into the calculator. And what you're going to wind up getting here is going to be a pH of 4.74. So when you add that to the 0 overall, the pH overall, we ignore the 0 part, so the pH is right here. So we see that the pH is 4.7. If you're asked to interpret what kind of solution you are at, because the pH is below 7, this particular pH here will indicate that the solution is acidic. All right, so let's keep going here. If I keep going on this, you'll see that there is a little bit more that we want to do. There is another example that I want to be able to do, and I might just grab that, put it on screen, and show it before I move on to 8.10. 8.10 is about buffer capacity, and I think I'll hold off. And so what I'll do here is I'm going to put the problem right here in this space, if not off screen, just so that we can have that information to do another example for you before you go. And then I'll probably put the next video probably as a separate video so it doesn't get too long, and that will allow me to upload different videos simultaneously while I keep generating them. All right, so here is the other problem that I brought forward. Let me make the space a little bit better. Let me move it up to the top. All right, so if we're solving the problem, I've already gone ahead and underlined some items. You can already tell that it's a buffered solution, and it contains a different concentration here. We've got NH3, and we've got a concentration of this thing called NH4, ammonium chloride. They're giving us a Kb value for the NH3. Notice the Kb value is -5, so it's a Kb value, so that means that this is the base, and it's actually dissociating very small amount. And they wanted us to find a couple of things. They want to know what are the identifying major species that are here in this reaction, and then subsequently find the pH. Is the solution acidic or basic based on that pH? So here's what we'll do. Since we are looking at the NH3 in solution, when you put the NH3, one of the reactions that you're going to get is you're going to get the NH3. That's going to react with the water. Now, since it's a base, it's going to be able to accept a proton, so it'll come in and take a proton from the water. So the water in this particular case is going to act as an acid, and we are going to end up getting here NH4. When it gains the proton, it gets a positive charge, and then you're going to generate hydroxide ion. That there, they're telling you that the Kb value for this is equal to 1.8 e to the -5. It's not a very big Kb value, but nonetheless, that's the reaction. The other thing that's in solution is a NH4Cl. reaction, a compound. So that one's going to dissociate. They don't give us any information about that. So typically when they don't give you a lot of information, it's not significant enough to mention. So a safe assumption would be that it's a very low value as well. So here the other reaction, let's call this reaction 1. The other reaction 2, is going to be for the NH4Cl, and it will engage a dissociation to generate NH4 plus ion and Cl minus ion. So here all I'll say here is it's a low K value, generic. And then the other thing in solution, since it is a solution in water and we have aqueous environment, there is a third reaction occurring here, and let's call that reaction 3, which is going to be the self-ionization of water. Water here we already know breaks down into H protons and hydroxide ions, and we know that the K value there, which is a Kw value, is equal to 1 times 10 to the negative 14. Also very small. All of these are really small. The smallest contributor of ions, in this case either proton or hydroxide, is the water, is very low. Since they didn't give us anything for the second reaction, we have to assume it's at least smaller than this number here. So the greatest contributor of ion in this solution is going to come from reaction number 1. So we'll use the values provided there. Again, a Henderson type problem. So what we'll do here is we'll move this up a little bit. And then I will put the work here on the side, or at least down below. I'm trying to kind of make some space here so that I can actually get things done a lot easier. So here, once we do that, we can identify the species. All right, so the next thing that we need to do is find out what's our acids and our bases. Now remember here, when we look at this, the pH equation coming back is going to be equal to the negative log of the Ka value plus the log of the concentration of that base versus the acid. Now the difficulty in doing this, that should probably stand out, is if this is the Henderson's equation, it's looking for a Ka value, but if we go right up here, notice we were given a Kb value. So we are literally going to need to kind of do something with this Kb value. The good news is that we already have some way of dealing with that. So what I'll do here is, let me just move this over a little bit to give us some space over here on the right. I'll just move that over slightly. And remember previously what we had learned was that the Kw equation was equal to the Ka times the Kb. So what we can do here is we can take this Kb value that's provided for us. We can take that and plug it in here. We already know the value of Kw, that's 1 to the negative 14, and when we do that, we can solve for that. So all I'm really saying is that we can do this. We can divide here by both sides, take Kb on both sides, that cancels on the right, and we'll need to divide by Kb on this side, so the Ka value will be equal to the Kw divided by the Kb. If we go ahead and substitute the values for Kw, well, we know that that value is going to be, let me go ahead and erase it. We can substitute that value, or erase that value here in the numerator. We can put the actual value that we know it to be. And so let's go and use, I guess I'll change it to a yellow. We know that that's 1 times 10 to the negative 14. And if I come in here and replace the K value for the Kb, that Kb value from above is 1.8 times 10 to the negative 5th. And so when you do the math like that, the Ka value now, we can calculate that, and that number for us is going to be, let's see here, the Ka is, plugging that in, that'll give us 5.56 times 10 to the negative 10, if you do it like that. And so now we're in a position where we can take this number Ka and we can plug it into the equation. We still need to identify the acid and the base, and for that we're going to have to come back up top and try to figure some stuff out. So having said that, let's kind of move things down so we can see it clearly. Now what exactly is the acid and what is the base? Well, since they gave us a Kb value, we already know that the NH3 is the base. Okay, so we can just go ahead and mark it as that. So let's go ahead and put this here. We can say here, this part here is the base. Now, where's the acid? Well, the acid in this particular case is going to be the NH4Cl. That's the other species, so deduction would tell you that. But why exactly is this the acid? Well, what's going to happen here, it's not depicted, but what will happen is that this NH4Cl, when it dissociates, we know that it's going to generate the NH4 and the Cl minus. So this NH4 then can react with the water in solution, and that is what will generate this proton in the form of H3O. The other product that you're going to get is NH3, is what's going to be generated there. So the base in this particular case is the NH3, but the acid, or the thing that eventually leads to the acid, is the NH4Cl. So if that's the case, we just plug things in, and let's go ahead and do that here. Let's move things up a bit. And if we plug everything in, the pH then is equal to the negative log of the Ka value, which we just figured out was 5.5 times 10 to the negative 10. And then we're going to add that to the log of the concentration of the acid and the base. And in this particular case, for the base is 0.25, and then the acid here is 0.40. When you plug all that numbers into the equations, your pH value here is going to end up being 9.05. And so that value there is essentially indicating that we have a basic solution. So the solution here is basic because the pH is above 7. So that is the remaining example that I have in this particular section. With that said, those are the main concepts there in 8.9. We're going to move on to the remaining two sections. They won't take me very long, but I'm going to go ahead and put them in a separate video so that I can at least get this video out. So having said that, we'll see you in the next video.